This is section 8.9, bond enthalpy. Okay, now what we're going to do is we're going to connect our discussion of energetics. We did that back in chapter 5. We're going to connect that to Lewis structures. It turns out that if you consider what's really happening in a chemical reaction, okay, let me show you what I mean by that. If I say that H2 is reacting with F2 to form 2HF. The energy change, there's some energy change with this, right? One way to figure that out would be to do a thermochemical experiment. We would run the reaction under controlled situation, and then we would measure how much heat was either released by the reaction, in this case, or absorbed by the reaction, a thermochemical reaction. But it turns out that the energetics of chemical reactions is really due to this issue of bond breaking and bond forming. It turns out that if you have two atoms and they're bound together, it's an endothermic process to break that bond. Okay? You have to put energy into that bond to break it. That's an endothermic process. But the process of forming a bond is an exothermic process. Okay, it's the opposite process, so it's the opposite thermochemical sign. So here delta H is positive. Here delta H would be negative. It's an exothermic process. Okay? So in the case, let me erase this. In the case of hydrogen, if we wanted to break the bond between the hydrogen atoms in a hydrogen molecule to form two hydrogen atoms, right? H plus H. Delta H for this process is 436.4 kilojoules per mole. It's an endothermic process. Okay? If I wanted to do the same thing for an oxygen-oxygen double bond to form two oxygen atoms, the amount of energy that it would take for that process is 498.7 kilojoules per mole. And we call that the bond enthalpy, the amount of energy it takes to break two atoms apart. And if you take a look at table 8.6, you'll see that table 8.6 has a bunch of tabulated values. Okay? Hydrogen, H2, I picked that up at the top there, 436.4 kilojoules per mole. Oxygen, oxygen double bond, 498.7 kilojoules per mole. Now, it's an endothermic process to break a bond. So that means that if you want to form a bond, take two oxygens and form oxygen-oxygen double bond, it's very easy to figure out what that would be. It's the opposite process, so it would be negative 498.7 kilojoules per mole. You remember from Hess's law we learned about that. If you reverse an equation, you change the sign of the enthalpy change. The same is true for bond enthalpy. And if we wanted to form a hydrogen molecule from two hydrogen atoms, we would just take our bond enthalpy and change the sign. Isn't that cool? Exothermic process. So we're going to sum this up by saying that bond breaking is endothermic. bond formation is exothermic. And so what happens is, if you consider a reaction such as 2H2 plus O2 goes to 2H2O. Now, all of this discussion is gas phase. Everything we're talking about here is gas phase. Those bond enthalpy values in table 8.6 are tabulated for gas phase chemical bonds, how much energy it takes to break chemical bonds in the gas phase, not solid or liquid or aqueous, okay? Now, here's what I'm going to say. This process is exothermic, okay? The formation of water from hydrogen and oxygen is, under normal circumstances, an exothermic process. And what I'm going to argue is the reason for that is that if you calculate the energy it takes to break these bonds, and then you calculate or measure the energy that gets released, sorry, misspelled, okay? So it takes energy to break the bonds, but you're going to get the energy out when you form the bonds, right? Because we're talking about bond formation here. We're forming chemical bonds here. Here we're breaking bonds. If you take the energy in and you subtract from that the energy you get out, it turns out it's less than 0, okay? And so it's an exothermic process, okay? Meaning you get more energy out than you put in. And that's essentially what an exothermic process is. If you put some energy in but you get more out, that's an exothermic process. So we can show by using the values in this table here that this is an exothermic process very easily. And so I'm going to go through it for you and show you the method by which we would do that. Here's what you do. You take your balanced equation and you draw Lewis structures for all the substances. Now for oxygen, the best Lewis structure is a double bond. Okay, not a single bond, but a double bond. And then the Lewis structure for water, that's pretty straightforward, octet, right? Now what I'm going to do is I'm going to indicate how many of those molecules are in the balanced equation. Because remember, we're measuring the delta H for the equation. There's 2 molecules of hydrogen, or 2 moles of hydrogen. Oops, 2. So I'm going to put a 2 there. That's a 1. And then there's a 2 there. Then what I'm going to do is I'm going to look up the bond enthalpy values. So for hydrogen, we've already talked about that. Oops. It's 436.4, okay? So 2 times 436.4. And then I'm going to add that to the second reactant. For oxygen, if you look for O2, it's 498.7. It's the one in pink, 498.7. And then I'm going to subtract the energy out. So minus, now here's the trick. For water, there's one bond, but there's a second. These are separate bonds. So we have to take both of those into account. So there's 2 bonds in one molecule, but there's also 2 molecules. So it's really 2 times 2 times the bond enthalpy. And for OH, it's 460, up there at the top on the left, 460. Okay? So energy in minus energy out. Now, if you go through this calculation, this becomes 72.8 plus 498.7 minus 4 times 460. Okay, so let me just do that here. 460 times 4. $18.40 there. Okay, did I get that right? 24.20. Oh, I think I did that wrong. Sorry. 460 times 4. 16, 18. Now that's 1840. Okay. So 872 plus 872.8 plus 498.7. So let's come through. Let's calculate that out. I'm going to open up my calculator here. Okay. There's our calculator. So it's 872.8 plus 498.7 minus 1840. And you get minus 468.5. Kilojoules per mole. It's negative, right? Exothermic. So the reason that this reaction is exothermic is because the bonds, all the bonds of the products, if you add up the bond enthalpies, are greater than the bond enthalpies of the reactants. So when a chemical reaction occurs, if all the bond enthalpies of the products are greater than the bond enthalpies of the reactants, energy in minus energy out will be negative, meaning it's an exothermic reaction, so you get energy out. Now let me show you the formula that's given in your textbook for this calculation. Delta H equals, it's under standard conditions, the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. Okay? So in other words, we're breaking bonds for the reactants and we're forming bonds for the products. So that allows us to use all the values in that table. I do want to point out one thing, which is that if you're doing the carbon-oxygen double bond, there are two values. If it's in CO2, because CO2 has double bonds, it's 799 kilojoules per mole. If it's C double bond O in some other molecule other than CO2, it's 745. Okay, so be careful with those calculations. If you're doing CO2, it's 799. If it's in a different type of molecule with CO, C double bond O, it's 745. And I also want to point out that if you're looking at O double bond O, we said that was 498.7. If you look at O single bond O, that's 142. And so if you think about it, if you try to do a trick and say, oh, well, a double bond is just twice of a single bond, that's not true. 2 times 142 would be 284. And that is not equal to 498.7. So you cannot say that, this is equal to this and this together, adding those two together. Be careful with that. You need to get the Lewis structure and know whether a bond is a single bond, a double bond, or a triple bond to be able to do those calculations correctly.